we're going to be talking about evaluating time complexity today. Just going to be a brief introduction to the idea. So, motivation for analyzing time complexity, pretty obvious. We want to know how long it will take our programs to run, and how long it will take our algorithms to run. If we know information about this, we can make services more reliable and faster by optimization and also accommodation. More specifically, however, we want to define an upper bound of the worst case runtime of an algorithm relative to some input n. And the reason why we want to focus in on the worst case runtime of an algorithm is because if we know the worst case runtime, then we can accommodate for the worst case runtime. And if we accommodate for the worst case runtime, we're going to be able to accommodate for every other case. So complexity is denoted by some expression where the only unknowns are the inputs to the algorithm being analyzed. So an example is, so what we mean by this is that we're going to create some expression within these parentheses that you can see at the bottom here, within parentheses, and that's preceded by a big O because this is called big O notation. The expression that we give is going to be relative to the input size n of our methods because we want to analyze their running time relative to how much they're given to work with or to work on. So for example, if a method f of n runs with an input size n in linear time or in, we'll define this later, but if it runs in linear time, then we would give this expression right here as notation of showing that. Okay, so an important point that you might have caught on with so far is that everything in time complexity is relative. We're not asking about just how long something will run, but how long it will run relative to what its input is. So a great example here are these two loops, where this function has a loop that runs n times, and this function has a loop that runs 1,000 n times. So this loop down here is obviously going to take longer to finish than this loop. However, when we say when we double n, what's gonna happen to the runtime of these two functions? Well, this function is going to go from n iterations to 2n iterations within this loop, and then this loop is going to go from 1,000 n iterations to 2,000 n iterations. So that means that the runtime of both of these loops scale directly with their input size, which means when n doubles, the amount of time it takes to run doubles. Same over here. So this is what complexity is getting at, is as the input size increases, how long does it take, how much longer does it take for the algorithm to run? So because these both scale directly, we'll denote both of these as running in big O of n time, or in linear time, because even though this one would finish much sooner than this one. So we'll walk through a few examples here. This is the sort of bog standard example for a polynomial time algorithm, or polynomial running time algorithm, which runs in or scales worse than a linear time algorithm like we saw before. And we can see that it runs in polynomial time because for any input size n, we're going to be running this inner code within this inner loop, within the outer loop. This code is going to be run n squared times because it's going to be run n times for every I from 0 to n. Yeah. So this would run in n squared time, and you can see again relative to n why this is true, because if we say have 2 here, it would do 4 iterations on this inner code. But then if we double that to 4, the number of iterations here would go from 4 to 16, which is 16 is not double 4, so it increases at a greater rate than linear.